Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection, as usual. Today, a bit of statistical mechanics without really doing statistical mechanics, we'll see. So there's a funny, notion, a funny constant, which is called the square ice constant, and that's roughly this number here, whatever. That's an explicit expression, you will see it in later, but it's related to ice. In some sense, we'll see how it's related to ice. And it came around, well, a little bit of background in the 50s, 60s of the last century. It's also called Leap's square ice constant. So roughly the 50s or 60s of the last century, roughly. And it's related to more and more physics, in particular, like quantum physics or quantum chemistry, something like that, being formulated in terms of mathematics. And here's another one from statistical mechanics, where you take some certain limit, as you will see, kind of to study a little system, and the system should model ice, but well, ice crystals, that's what we model, are really huge in the sense, well, of course, they're not really huge, but they're huge from the viewpoint of, well, the tiny particles. And then you need to take the system to infinity, and as a limit, you will find this number 1.596, which is then related to the entropy and other physical properties of the system, which we're not going to address because it's too much physics for me. But it's still very interesting. So in the sense that, again, kind of mathematics and physics go hand in hand here, and has a really funny constant lurking around coming from looking at ice. Okay, so let me give you some background. So I love this bubble, which I stole from a very nice summary paper about statistical mechanics, which I link in the description. So statistical mechanics is kind of the bubble outside, and it's kind of relevant for all other fields of physics. So here are the four main fields of physics, let's say. And I really love this picture because I was never really sure what quantum field theory is. But in this picture, it's quite clear. It's just very fast and very small. So classical mechanics is slow and big. Relativistic mechanics is fast and big. Quantum mechanics is small and slow. And quantum field theory is, well, very fast and very slow. Very fast and very small. Anyway, so the point is, we're not talking about quantum field theory anyway. We're going to talk about a bit about statistical mechanics. And this is this idea to study macro states instead of microstates. So you just think of having a box of little gas particles, and instead of studying the motions of each gas particle separately, which is kind of hopeless, you study the behavior of the system. And because you have plenty of them, kind of quite a few gas particles within the box, the correct way, in some sense, correct in huge quotation marks, way of studying those physical systems is to use some kind of statistical properties. And well, we'll see actually in a very specific example what that means. And the point is, we always kind of want to model a system at hand, and that's what we want to do, whatever, usually simplified, because life is just too complicated for physics, and life is way too complicated for me anyway. But some simplified model of the world. In this case, what a surprise, it's about this ice constant here. So it will be about ice, or a certain form of ice. And usually, and it's kind of fun, and it's not quite clear to me why, but it turns out that experience tells us that a lot of real world models that you kind of model, not just in statistical mechanics, but also in statistical mechanics, they really need to really nice mathematics. So in some sense, we can then ignore the real world models, which we shouldn't, but we could, and just focus on the nice mathematics. And that's what I'm certainly going to do in this video, although really, in some sense, we shouldn't forget about the real world models, of course. Okay, so this is kind of the setup. Without going too much into details here, what statistical mechanics and what kind of questions are addressed in general. Again, with respect to, there's a link to a nice summary paper in the description, where I also stole all these funny pictures from. Okay, so here's the setup in a little bit more details. What we want to study is ice. And we kind of really ignore whether this makes sense in the sense of the real world. We'll comment on that later on. But for now, I just want to study ice, and I think of it as living on a square grid. That's where the name square ice comes from, with the oxygen. So these guys are the oxygen ones. They're always so this is a part of the squared, and they are always at the corresponding lattice points. And you could think of the hydrogen ones as being the edges between them. So you get, for example, this picture. That's how they could arrange. Like this oxygen molecule here goes a little bit like this. And let's say this point here, the oxygen one is 0, 0 somewhere. And then you get a whole lattice of them. Okay. And because we don't like infinite systems anyway, we kind of study only in n by n square. So here is 3 by 3 square. So the number 3 is counting the oxygen atoms in each row and column. So it's 3 by 3 grid. And we want an orientation on that lattice corresponding to the arrangement of the lattice itself. So here's the easiest to see. So these are the vertices, right? So, but now at each, should be an edge. And there are two ways how this could look like. It could look like this in this case, with nothing here, or it could look like this. So the edge could belongs to one of the O's. It could look like this or like this, and we put in orientation depending on how it looks like, and then we just count the number of orientations, or just we have an oriented graph. So this points upwards because we have this situation, and this points downwards here because we have this situation here, the other way around. Similarly for left and right. Okay, so what we get here in this model, after we have forgotten everything about ice and whatever, it's just a square graph, n by n, and an orientation on the square graph. Relatively simple. Before we go on, let me comment how realistic that actually is. So here's a Mathematica demonstration about crystals of ice. So ice forms different crystals, but the most common one looks a little bit like this. So locally, it's more like a hexagon type picture. So it's really the same picture that we had before, but now the hydrogen atoms are just edges, and there should be orientation on the edges, but this program doesn't have any orientations. And then they arrange themselves in those hexagonal patterns here, which is quite different from what we are looking at, and it's really a simplified picture we are looking at. So this is kind of a way more realistic. This is a really good viewpoint here. A way more realistic ice crystal where you see hexagonal patterns, and it's certainly also three-dimensional instead of two-dimensional. Okay, but again, we kind of ignore whether this really makes sense. Just the square is just easier than a hexagon pattern, and two-dimensional is certainly easier than three-dimensional. So we just stay with this picture for now and see what we can say. Right? Turns out that all others are just so much harder. So let's really just stay with this picture right now. Okay, and in order to avoid boundary nonsense, we want to go to infinity anyway. We think of the picture as living on a torus, in the sense that going out here, you will re-enter here, and going out here, you will re-enter here. But since we take n to infinity anyway, it doesn't really matter. It's just a comment here. So if you're an expert and know what boundary conditions are, these would be periodic boundary conditions. Anyway, so what we are looking for is what is called an Eulerian orientation. So that's each vertex has two incoming and two outgoing edges. Why do we want that? Well, think of it like this. Each vertex has two incoming and two outgoing edges. And this is just because of the configuration with the H atoms, because you have two adjacent H atoms, and they are always the ingoing edges, and you have two, well, kind of adjacent but not connected H atoms, and these are the outgoing edges. So these, whatever, the Eulerian orientation is what makes physically sense. And we just want to count the number of those, because this is kind of the number of possible states of the system. Right? So the system will always have a state with two incoming and two outgoing edges, but there can be many states for the same system. We'll see an example in a second. And the mathematical goal is simply to count the number of those as n goes to infinity. So not for a fixed n, but as n goes to infinity. And it turns out that this is a nice answer, which is absolutely non-trivial at all. And here's the answer. And this is the square ice constant then. So Fn is the number of Eulerian orientations of the n by n grid. And of course, the Fn itself approaches infinity. But if you take the 2nth root, that makes some physical sense, you actually get a limit. And the limit is this number here, whatever, it's 1.54, let's say. And this is called the square ice constant, and it's related to the entropy of the system. So let me give you an example here explicitly. For n equals 3, F3 is 7, and here are the 7 different orientations that fit for the n by n grid. And Fn obviously I mean, you count number of things and it goes bigger and bigger and bigger. And it's not hard to convince yourself that it actually approaches infinity. And there's some brilliance involved to just take the correct limit and get a number out of it that actually resembles something in the real world. And the corresponding keyword here is called the six vertex model. So six vertex, simply because the six local configurations, you have one that looks like this. And so 2 in, 2 out, and times 4, so 4 rotations of those, and you have one that looks like this, and so 2 in, 2 out, and 2 possible versions of these. That's why it's called the 6 vertex model, and they play slightly different roles, but today that's not really important. So we count the number of those, and we get a constant which resembles something in the real world, which is kind of a very cool thing. And again, coming back to my picture, that actually ice doesn't really form a square, but most often more like a hexagon. And maybe even more important, we should study the problem in z cubed, or instead of z squared, because it's 3-dimensional. As far as I know, all other lattices, more complicated lattices, we don't want to do simpler lattices, so you can do the z lattice yourself if you want. That's not so hard. But all other bigger lattices, the real ice lattices, are very difficult, and I don't know any good answer. There is this whole story of solvable lattice models, and solvable lattice models is exactly what it says. And solvable means that you can write down a closed formula for whatever you call a solution, and this is one of them. So here's a closed formula. It's really nice, actually. It's not so bad. But for all others, this is kind of out of reach, for all other more complicated ones. And that's why it's a little bit sad. So nature is slightly more complicated than actually the model, but we still get a cool answer here. And it's kind of still a nice mixture between mathematics and physics, statistical physics. And people use that, actually. It's kind of cool. So what you can do is very different. People ask questions about certain tilings, which are related to a certain matrix conjecture. Here's a picture of such a tiling. And then there's a relationship between the 6 local states, right? Those 6 here, and the 6 tilings that you can draw. So maybe I can try here. So there's this little tiling block here, which looks a little bit like this. Really bad picture. And you have 4 of them. You can turn them. So here's one, here's another one. So let me try to find them. Here's another one. And here's another one. So the 4, so here's one, the 4 different. And then there's those 4. And then the funny ones correspond to tilings that look like this, and one that's sitting on the side. So let me try to draw that actually. Okay, so these are the times, these are the 2. And this corresponds to a tiling, which you can nicely illustrate here. This is an example of a much bigger grid, and that actually is an FN coloring in Eulerian Orientation, just translated from this picture here to the tiling picture, and then put in some nice colors. So there are 6 different ones, so you can put six colors here. Anyway, so there was a very different question related to those tilings, and you can actually use the ice constant, or at least the ice model, proof to write down a proof for this alternating sign matrix conjecture, with more details linked in the description. Anyway, so this is kind of just the tip of the iceberg of a huge connection between various forms of physics, real-world models, and kind of nice mathematics. So we get out a pretty cool constant which counts something in the real world, if you would like to say that the ice model is a real-world model anyway. But it also is a nice solution of a counting problem in, let's say, in extremal graph theory or something. So it gives you a very nice constant, and it's part of the story of solvable lattice models. Anyway, I hope you enjoyed the video, and I also hope to see you next time.